In section 1.8, we're going to come back and review other types of inequalities. Inequalities is something that we did earlier in the class, but in particular, what we're going to be doing now in Unit 3 is we're going to be looking at two very special types of inequalities. Those that involve polynomials, which was our focus for Chapter 3, as well as rational inequalities, which was the focus for Chapter 4. And so in a lot of senses, it kind of makes the ordering a lot better now that we kind of covered these two types of inequalities, having a much more in-depth review of what polynomials and rational functions are. The first type we're going to look at is polynomial inequality. A polynomial inequality is any inequality that can be put in the form f of x compared to 0 with one of the four basic inequality signs in between it. Less than, greater than, less than or equal to, or greater than or equal to, where f is a polynomial. So essentially what you're doing is you're getting all of the terms to one side, and then if you have a polynomial being compared to 0, that's what makes it a polynomial inequality. The procedure for solving a polynomial inequality is the first step is to express the inequality in one of the four forms above, i.e. we want to start by setting one side equal to 0. Once we have one side equal to 0, that other side, we're going to call that the function f of x, it's our polynomial. We want to solve the associated equation f of x equals to 0. These solutions x to this equation will be referred to as the boundary points. From there, what we will do is we will plot the boundary points on a number line that will divide the number line into intervals, and then what we're going to do is pick a test value within each interval and plug it into the polynomial f. If the value of f is positive at a test point, then the function f of x will be positive for all values of x in that interval. If the value of f is negative, then f of x will be less than 0 for all values of x in the interval. This is a consequence of the reason why this test works is one of the things that we know about the graph of a polynomial function is that polynomials are continuous functions. And we said that continuity, even though we didn't focus on it too much, the intuitive idea behind continuity is that you're able to graph the function without lifting your pencil off the paper. So if it's going to be the case that a polynomial is going to change its sign, meaning from negative to positive, wherever the polynomial would be below the x-axis, these would be where it would give us negative values. Okay, so the sign of the polynomial would be negative below, and wherever the graph of the polynomial is above the x-axis, this would be where the polynomial is positive. And the only places where a polynomial, because it's continuous, in order to switch from negative to positive or vice versa, via something called the intermediate value theorem, which we're not going to talk about too much, but because it's continuous, that means that it must pass through 0. That's why the boundary points are so important. Those are the potential places where the sign of a polynomial can switch. Other than that, if you look between the boundary points, the polynomial will have consistent sign in between those boundary points. So that's the reason why this method works. Let's go ahead and take a look at one. In example 1, we're asked to solve and graph the solution set on the real number line. We have 2x squared plus x is greater than 15. So to begin, we want to put it in standard form. We need to get one side to be 0. So let's go ahead and subtract 15 to both sides. This gives us 2x squared plus x minus 15 is greater than 0. This portion of it on the right-hand side, that's the thing that we're going to label f of x. So let f of x equal 2x squared plus x minus 15, and we're now going to use that to find our boundary points. To find the boundary points, we're going to set this thing equal to 0. 2x squared plus x minus 15 equals to 0. Fortunately for us, this should factor. It's going to be a 2x and an x. We will try a 5 and a 3, and it should be a plus and a minus. If you're not sure, you can check this if you distribute it back out, but the outer terms will give us a 2x times 3, which would be 6x, and negative 5 times x will give us negative 5x, and then the 6x and the negative 5x do add up to the positive x in the middle. So we factored it. We can now go ahead and set each factor equal to 0 independently. For this first one, we're going to add 5 to both sides. We get 2x equals to 5. Divide both sides by 2. And so we get one boundary point is going to be x equals 5 halves. Over here, we would subtract 3 from both sides, and we would get the second boundary point, x equals to negative 3. So those are our two boundary points, 5 halves and negative 3. Let me do a little bit of erasing so we're able to squeeze some more work onto here. So again, this inequality was 2x squared plus x minus 15 was greater than 0. And now what we're going to do is we're going to plot these on a number line. So if I plot these two numbers, it turns out that two values, the negative 3, make sure you plot them in order, by the way. So going from left to right, the negative 3 would come first, and then we would have our, that what looks to be an ugly looking 5 halves. Let me clean that up. There we go. And negative 3 and 5 halves. Two numbers will divide the number line into 3 regions. Okay. Let's kind of go ahead and we'll highlight those. See if I can find a nice color. And let's go ahead and do, we'll do orange. Okay. So we have region 1, region 2, and we have region 3. We have region 1, which is the region to the left of both points. Region 2 is the region in between the two boundary points. And region 3 would be the region to the right of both boundary points. We are now going to use the method of test points. What we are going to do is pick a test point within each region. And we're going to plug it into the function. For example, in region 1, I see a value of x that would be in there, would be the value x equals to negative 4. So let me go ahead and I'm going to plug x equals negative 4 into the function. Our f of x, again, by the way, f of x was 2x squared plus x minus 15. So f of negative 4 is going to be equal to 2 times negative 4 squared plus negative 4 minus 15. If we work this out, negative 4 squared is positive 16 times 2 is going to be 32 minus 4 minus 15. 32 minus 4 is 28, and then 28 minus 15 will be 13. Okay. At this point, when it comes to the test points, we don't really care so much what the actual value is. We're more concerned with the sign of it. Okay. 13 is greater than 0, which in particular is a positive value. So in region 1, the function values, f of x values, are always going to be positive. Let's test region 2. Whenever you're able to, 0 is always a nice test point, and that happens to lie in region 2. F of 0 is equal to 2 times 0 squared plus 0 minus 15, which is equal to negative 15, which is less than 0. Because the function f is 0 at the test point 0, that is negative at the test point 0, that means that the function will always be negative in region 2. And now lastly, we need a test point in region 3. 5 over 2, that's 5 halves, which is the same thing as 2.5. So we could use anything bigger than 2.5. Let's say x equals to 3. If we evaluate f at 3, this is going to be 2 times 3 squared plus 3 minus 15. 3 squared is 9. 9 times 2 is 18. So we have 18 plus 3, which is 21. And then 21 minus 15 would give us 6. And that's going to be greater than 0. Because the function is positive at that test point, it's going to be positive everywhere within that entire interval. And now that we've done this, we're able to go ahead and write out the solution set. To determine the solution set, we need to look at which direction the inequality is facing. So coming back to the beginning, notice that we set f of x equal to this thing. So we're looking for the solutions where f of x is going to be greater than 0, i.e. we need the intervals where it's going to be positive. The function f is positive on this interval here, region 1, and it's positive on region 3 as well. The other thing, and we probably should have done this a little bit earlier, is we need to also determine what's going to happen at our endpoints. So one of the questions we need to determine is, will the boundary points be included or not included in our solution set? And the answer depends a lot of times on the type of inequality that you have. Here, notice that this is a strict inequality. This is the statement that x is strictly greater than 0. At each of those boundary points, those are precisely the points where the function value equals to 0. Because 0 is not included here, because it's not a greater than or equal to, that means that we cannot include the boundary points. So those would be open circles. And now that we're ready to write out our interval notation, we'll see how that's going to look. So the solution set includes intervals 1 and 3. That is everything from negative infinity up to including negative, up to but not including negative 3. And then union, we have everything that doesn't include 5 halves and to the right towards positive infinity. As we saw before, whenever we're talking about interval notation, that's the proper way to represent the solution set to an inequality. And for the graphed interval, this is what it would look like. So it's everything like this, and those endpoints are not included. So just to kind of recap, what were the steps to solve this polynomial equation? Step 1, we want to get it in standard form. That means we want to set one side equal to 0. Step 2 is we want to let f of x equal that polynomial part on the left-hand side. After that, step 3 is to find these boundary points. So you set f of x equal to 0 and solve. We then plot those boundary points on a number line and determine how many different regions we have. Step 4 is picking a test point or a representative within each region to determine the sign of the function f. So you pick a test point, you plug it into the function, you get a value, and whatever the sign of that value is, that will be the sign of that value consistently within that region. Once we know all of the signs or the sign chart for the function f, to pick the appropriate solution set, we need to consider the type of inequality that we have. Here, because it was a greater than 0, we wanted all of the intervals where the function was positive. If the inequality had gone in the other direction, if it had been like f of x less than 0, then we would have been looking for the intervals where the function f is negative. The other consideration when wrapping things up is we need to determine whether these boundary points will be included or not included. And for the polynomial inequality, it depends upon the type of inequality that we have. If we have, for example, a less than or equal to or a greater than or equal to, then the endpoints will be included. They'll be filled in circles, which will lead to brackets in our interval notation. If, however, like the last example, if it's a strict inequality, that means that those boundary points will not be included. So that would be open circles, and it will lead to open parentheses in our interval notation. Let's take a look at another one. In example 2, we want to solve and graph the solution set on a real number line. We have the polynomial inequality x cubed plus 3x squared is less than or equal to x plus 3. First things first, we want to get one side to be 0. So let's subtract x and also subtract 3 from that right-hand side. The x and the negative x, the 3 and the negative 3 will cancel. So we get 0 on the right-hand side. On the left-hand side, we don't have any like terms, but we can at least write it in decreasing order. We have an x cubed. We have a plus 3x squared term. We have a negative x. And then we will have a minus 3. Now that it's in standard form, we're going to let f of x be that polynomial on the left-hand side. So let's let f of x equal x cubed plus 3x squared minus x minus 3. And now the next step is to find the boundary points. To find the boundary points, we set f of x equal to 0. Like this, and now we need to solve. The easiest and best way when it's possible to solve a polynomial equation is hopefully to be able to factor this thing. Here this is a polynomial of degree 3, but notice that we have 1, 2, 3, 4 terms. And if we have 4 terms, the method of factoring we should always try, at least at first, is to try to do a factor by grouping. So let's group the first 2 terms together and the last 2 terms together. We have x cubed plus 3x squared minus x minus 3. We can pull a GCF of x squared out of the first parenthesis. That'll leave us with the x plus 3. We can pull a negative 1, which is the GCF out of those, but because the first term is negative, you want to factor out the negative of the GCF, so pull out a negative 1. We now have 2 terms, both of which have a common factor of x plus 3. So let's factor that out. This will leave us with x squared minus 1 equals to 0. And now notice that once we've done that, we have a partial factorization. This term here that we get actually happens to be a difference of squares. So that will factor as x plus 1 times x minus 1 equals to 0. And now we can set each of these factors equal to 0 individually. If you set the first factor equal to 0, that's going to give us x equals negative 3. If you set this factor equal to 0, that'll give us x equals to negative 1. And if we set this factor equal to 0, we will get x equals to 1. So on this particular example, we have 3 boundary points. They are negative 3, negative 1, and positive 1. We are now going to go ahead and plot those 3 numbers on a number line. So we have negative 3, negative 1, and positive 1. One of the things that we kind of waited till the end of the last problem is we waited to see whether or not those boundary points would be included or not included. Let's immediately come over here and look at the type of inequality that we have. Here, this is a less than or equal to, and because of that component, the equal to component, that means that these boundary points will be able to be included in the solution set. Those 3 boundary points, by the way, will break up the number line into 1, 2, 3, 4 different regions. We're now going to proceed with the method of testing points. We need a test point for each region. In region 1, we need a number that's less than negative 3. I would probably use x equals to negative 4. In region 2, it might make sense to do -2. In region 3, I'll use x equals to 0, because that's available. And in region 4, I'm going to use x equals to 2. Again, it doesn't matter what test point you have, because the polynomial will have a consistent sign within each region. You can use any point in that region as a test point. So if you use like a -5, whereas I use -4, it's not going to make a difference. If our 2 points are in the same region, then regardless of what you pick or what I pick, that function will give us the same output in terms of its sign. So what we now do is I'm going to evaluate the function f at -4. So I plug -4 into the function. That's going to be -4 cubed plus 3 times -4 squared minus a -4 minus 3. -4 cubed is -64. -4 squared is a positive 16 times 3 is 48. That would be then plus 4 minus 3. -64 plus 48 is a -16. -16 plus 4 is -12. And -12 minus 3 is going to be -15. So we find that for f of -4, we get -15. So in region 1, the function is going to be negative there. You would then repeat this. I'm just going to skip a little bit of the work. If you plug -2 into f, I guarantee that it's going to be positive. So in region 2, the function is going to be positive. If you plug 0 in, we can do this one pretty quick. If you were to evaluate the function at 0, we would get 0 cubed plus 3 times 0 squared minus 0 minus 3, which is -3. So f of 0 is negative. So the function is negative here, which is in region 3. And then if you test it, for example, if you use the test point 2, you should find that f of 2 is going to be positive, which is greater than 0. Okay. Like this. So now we have our intervals. We're ready to go ahead and write out the solution set. Our inequality is of the form f of x is less than or equal to 0. That means that we're going to look for the intervals where the function is negative. That should be region 1, and then also again at region 3. And because it's less than or equal to, we also know that those endpoints of those boundary points will be included. So our solution set to this problem is the following. It's going to be the interval from -∞ to -3. I'll just try to squeeze that up here. -∞ up to and including -3. So that gets a bracket, union, everything between -1 and 1 also included. One of the things that you can sometimes do, and for those of you that feel comfortable with this material, you can actually do this. It's kind of a reasonableness check. So on the test, when you show your work, I absolutely want to see all of this work shown thoroughly, where you kind of plug things in and whatnot. But if you remember when we talked about polynomials and the multiplicity of a 0, if you look at our 3 boundary points, the -1, -3, -1, and +1, each one of these came from a factor with an odd multiplicity, right? This is to the first power, and first power. And one of the things that we recall is that if you have a 0 of odd multiplicity, then what that means is that that function is going to actually cross the x-axis at that 0. So it's going to cross here, it's going to cross there, and it's going to cross there. So for example, if you know in region 1, for instance, that the function is negative, by knowing the multiplicity of each of the remaining boundary points, you can actually tell whether or not it's going to switch to go positive to negative or vice versa. just by whether or not it has to cross through the x-axis at that boundary point. And if you kind of apply that method, that would actually save you, in theory, some of the computational work as an alternative approach to having to do test point calculations. Let's take a look at the next few examples. So example 3 is kind of 4 mini examples in one that just show some unusual solution sets that can occur when we're trying to solve these types of inequalities. If we look at example A, this inequality is already in standard form. We have one side is 0. So we're going to let f of x equal to the polynomial part. It's x squared plus 2x plus 4. If we try to find the boundary point on this one, we would set it equal to 0. And you can try for a couple minutes, but this thing is not going to factor. So to find the zeros, we would be forced to use the quadratic formula. It's going to be negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And as we're working it out, if you look at the inside of the square root, that's going to be 4 minus 16, which is negative 12 divided by 2. This is going to be a complex number. Because of the presence of the square root of a negative. On the number line, we're only able to plot real values, and so we would say that this equation here has no real solution. So there is no real solution to this equation, meaning there are no boundary points. What that means in terms of our polynomial inequality is that there is nothing to divide the real number line. So we get just one region, which is the entire number line itself, which means that the solution set to this problem is going to be either like an all or nothing scenario. Either every value of x will work, or no values of x are going to work. To see what we get, let's pick a test point. You can use any point. Probably makes sense to do x equals to 0. If we evaluate the function at 0, f of 0 is going to be equal to 0 squared plus 2 times 0 plus 4. And so we get that f of 0 is 4, which is positive. So this function is always going to be positive. It's positive on the entire real number line. However, because of the type of inequality we have, we're looking for f of x is less than 0. So we need the intervals on which f would be negative, and there aren't going to be any. And for that reason, this inequality is going to have no solution. So example A, 3a, is an example of a inequality, a quadratic inequality with no solution. If we look at example B, once again, it's already in standard form. We have one side to 0, so let f of x equal x squared plus 2x plus 1. This will have some boundary points. If we set x squared plus 2x plus 1 equal to 0, this does factor as x plus 1 times x plus 1, which is equal to 0. So we get x equals to negative 1 would be our solution to this, and it's a solution with multiplicity 2. We can now take and plot this number on the number line. Here's our boundary point, negative 1. Before we go any further, let's determine whether or not that boundary point will be included or not included in our solution set. Here, because of the less than or equal to 0, that means that it will be included. So we have at least one point that works, and that's the point negative 1. From here, we now want to look at our different intervals. We have two distinct intervals. We have region 1 and region 2. We're again going to pick a test point. In region 1, I would be inclined to maybe use the test point x equals to negative 2. If you evaluate f at negative 2, I'm just going to try to do this mentally. Negative 2 squared is 4. 2 times negative 2 is positive 4. 4 and negative 4 cancel, so we're left with plus 1. So in region 1, it's going to be positive, because we get 1. In region 2, I'd pick a test point here. I would probably use x equals to 0. And I'll leave it up to you, but if you plug in 0, you're going to get 1 out, which is, again, positive. So it's positive in region 1, positive in region 2. To write down our final solution set, let's come back here and look at the direction of the inequality. This inequality is of the form less than or equal to 0. So we would need the intervals on which the function is negative, and there aren't any intervals. All we end up with is a single point, and that's going to be the point x equals to negative 1. So a little bit unorthodox, but it turns out that for this particular inequality, we get exactly one solution, which is just a singular number, x equals to negative 1. Let's take a look at the next example. In example C, we have x squared plus 3x plus 5 is less than 0. Once again, it's already in standard form because we have one side to be 0. Let's let f of x equal x squared plus 3x plus 5. Let's find our boundary points. We're going to set the function equal to 0. Once again, this is one that's not going to factor. So let's go ahead and use the quadratic formula. It's going to be negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. If we look inside of this radical, it's going to be 9 minus 20, which is negative 11. Once again, this is going to be a complex number. This piece of it by itself, the piece itself is imaginary, but we get a complex number, i.e. this equation has no real solution. So we're once again in the situation where there's no numbers, no boundary points to plot on our number line, so we get the entire number line as just a singular region. You can pick any test point you would like. 0 is always nice. If we evaluate the function f at 0, if you plug in 0, it's going to be 0 squared plus 3 times 0 plus 5, but that should be equal to 5, which is positive. So this function is always positive. If we look at the direction of the inequality, though, however, we were looking for the values where it was supposed to be less than 0 or negative. So this is yet another example of one that's going to have no solution. So this one has no solution. Lastly, let's take a look at D. It's x squared minus 4x plus 5 is greater than 0. It's in standard form, so one side is equal to 0. So let f of x equal that polynomial. We're going to find our boundary points by setting it equal to 0. This factors as x minus 2 times x minus 2 equals to 0. Set each factor equal to 0 individually. We get x equals 2 is going to be a solution of order 2. That's one number to plot on the number line. So let's plot the number 2. Notice that because of the type of inequality, it's a strict inequality, has to be strictly greater than. That means that that value will not be included. So let's go ahead and put an open circle there to remind ourselves that it is not going to be included. That one number divides the number line into two regions, region 1 and region 2. We're going to pick a test point in each region. In region 1, I would use the test point x equals to 0. If you evaluate f at 0, I'll skip a little bit of the calculation, but f of 0 should be equal to 4, which is going to be positive. So it's positive in region 1. In region 2, we could use the test point, for example, 3. If you plug 3 into the function, that would be 3 squared, which is 9, minus 12 would be negative 3, plus 4 would be positive 1. So it's also going to be positive in region 2. If we go to look for the solution set, the type of inequality we have is greater than. So that means that we need the intervals where the function is positive. And that's going to be both region 1 and region 2. So we see that the solution set, it's going to include all real numbers with the exception of 2, which doesn't work because at 2 it's exactly equal to 0, but the inequality says that you have to be strictly greater than 0. So the solution set for this one would be everything from negative infinity up to, but not including 2, and then union, everything starting immediately after 2, and then towards positive infinity. So this is kind of a special type. It turns out that the solution set is all real numbers with the exception of a singular point. The last type of inequality we're going to look at in this section is what's called a rational inequality. A rational inequality is any inequality that can be put into one of the following forms: f of x less than 0, f of x greater than 0, f of x less than or equal to 0, or f of x greater than or equal to 0, where the f of x function is a rational function. The procedure for solving rational inequalities is going to be the following. We want to express one side as a single rational equation, right, as a single rational function, and we want the other side to be 0. From there, we're going to find our boundary points by doing two things. We need to set the numerator equal to 0 and solve. We also need to set the denominator equal to 0 and solve. We locate these boundary points on a number line that will again divide the number line into a bunch of different intervals. And we once again pick a test value within each interval to determine the sign of the function f. If f is positive at the test point, then it will be positive for all values of x in that interval. If f is negative, then f of x will be less than 0 for all numbers of x in the interval. And then lastly, we're going to write the solution set by selecting the interval or intervals that satisfy the given inequality. For the boundary points, to determine whether or not they're going to be included or not included, we need to look at a couple of types of things here. First of all, if you have one of the first two types of inequalities, if it's strictly less than or strictly greater than, then none of the boundary points will ever be part of the solution set. If we have one of the last two types of inequalities, meaning less than or equal to or greater than or equal to, then some of our boundary points can be included in the solution set. Namely, those boundary points that came from setting the numerator equal to 0, those would be boundary points in this case that would be allowed to be included because those would actually make the rational function exactly equal to 0, and that would satisfy those last two types of inequalities. On the other hand, if you have a boundary point that made a denominator equal to 0, those types of boundary points can never be included because those values of the function f would be undefined for. Let's take a look at an example of one. In example 4, we're asked to solve and graph the solution set. We have x plus 4 divided by x minus 3 is greater than or equal to 0. Notice that it's already in standard form. We have one side to be 0, and we have a single fraction on the other side. So let's let f of x equal x plus 4 divided by x minus 3. We are now going to go through the process of finding our boundary points. We set the numerator equal to 0. That is x plus 4 equals to 0. Subtract 4 from both sides, and we get x equals to negative 4. We set the denominator equal to 0. That is x minus 3 equals to 0. We add 3 to both sides and we get x equals to. Let's now go ahead and plot our boundary points on a number line. We have -4. We have +3. These two boundary points divide the line into 3 distinct regions. And before we go any further, let's determine whether or not any of these boundary points could potentially be included or not included in our solution set. First, we would want to go ahead and look at the type of inequality that we have. It's of the form greater than or equal to. So because of that equality component, it is possible to include some of these boundary points. For instance, we know that -4 is a value that makes the numerator equal to 0, and so that will make the fraction equal to 0, and that will be part of the solution set. However, the value x equals to 3, where did that come from? That was a boundary point that came from a result of making the denominator equal to 0. At x equals to 3, if you were to plug that in, we would get division by 0, which means that this function would be undefined there. So that type of boundary point can never be included. Any value that ever makes the denominator equal to 0 can never be part of the solution set. So we're here. Let's now go ahead and use the method of test points. In region 1, I would probably use the test point x equals to -5. Let's go ahead and plug that into our function. F of -5 is -5 plus 4 divided by -5 minus 3. That is -1 over -8, which is +1/8, which is positive. So in region 1, the rational function is positive. In region 2, let's use the test point x equals to 0. F of 0 would be 0 plus 4 over 0 minus 3, which is -4/3, which is less than 0. So in region 2, the function's negative. And in region 3, we can use the test point x equals to 4. F of 4 is going to be 4 plus 4 divided by 4 minus 3, which is 8 over 1, which is 8, which is greater than 0 and positive. Now that we know the sign, let's go back to the original inequality. We're looking for the ones that are greater than or equal to, so we want the positive intervals. That's going to be region 1 and region 3. We can now go ahead and write out the solution set. It's going to be everything from -infinity up to and including -4, union, not including 3, to positive infinity. Let's take a look at example 5. We want to solve the inequality 2x minus 7 divided by x minus 5 is less than 3. Notice that to begin, this is not in standard form. We do not have one side to be 0. So let's begin by subtracting 3 from both sides. We get 2x minus 7 over x minus 5 minus 3 is less than 0. The next step is we need to combine that left-hand side into a single fraction. So we need to get a common denominator. The 3 we can think of as 3 over 1. The common denominator is going to be x minus 5. So with that fraction 3 over 1, what we would need to do is multiply numerator and denominator by x minus 5, and that will produce 3x minus 15. So we get a common denominator. That will now allow us to subtract the numerators. It's going to be 2x minus 7 minus 3x minus 15 is less than 0. That is 2x minus 7 minus 3x plus 15 over x minus 5 is less than 0, which is going to be negative x plus, this looks like 8, all divided by x minus 5 is less than 0. So we now have one side to be 0, so we can set f of x equal to the rational function, negative x plus 8 divided by x minus 5. Let's now find our boundary points. We do that by setting the numerator equal to 0. Easiest way is to probably add x to both sides. We get 8 is equal to x. We can also set the denominator equal to 0, add 5 to both sides, and we get x equals 2 to 5. So we have two boundary points in order. They are 5 and 8. Before we go any further, notice that we're going to have three regions. 1, 2, 3. Let's determine whether or not these boundary points can be included. First of all, this one here, x equals to 5, that came from a 0 of the denominator, so obviously that won't be able to be included. But furthermore, if you look at the type of inequality that we have, because it's strictly less than, no boundary points anyway would ever be able to be included because it's the type of inequality. So neither of these is going to be included. We can now use the method of test points. In region 1, I would probably use x equals to 0. F of 0 is going to be negative 0 plus 8 over 0 minus 5, which is going to be a negative 8 fifths. So it's less than 0. It's negative in region 1. In region 2, sorry, I have to move the work over here. I would probably use the test point x equals to 6. F of 6, if you plug it in, would give us 2 over 1, which is 2. So it's going to be positive here. And then let's try and find somewhere to work it. Let's plug in test point in 3. I would probably use x equals to 9. F of 9 is going to be equal to negative 1 over 4, which is negative. So we now know the sign. Let's look at the direction of the inequality. Because it's less than, we need the intervals where the function is negative. That should be regions 1 and 3. So our solution set is going to be negative infinity to 5 not included, union 8 to infinity. Where again the 8 is also not included.